In this video I want to cover a couple of important vector concepts in 3 dimensions. So the first is the idea of using polar form for vectors in 3 dimensions, and then the second one is extending our understanding of the dot product to vectors in 3 dimensions. So just as we start this off, because in 3 dimensions it's often quite difficult to visualize sort of vectors when we're drawing them on a 2-dimensional page or a 2-dimensional space. So typically we express our z-axis as being the vertical axis, and then our x and y axes are in a kind of horizontal plane here. So if you can imagine, probably should have put the z-axis on last. But if you can kind of imagine the x and y axes there as sort of lying horizontally on the page, and then the z-axis is sticking perpendicular through our page or through that plane. Now those axes have positive and negative directions, but typically when we draw these, we actually don't show the negative part of the axis, and that's just to make life kind of a little bit easier because there's so many lines on the page. Let's just start off by thinking about our x and y axes lying down on the page. So if we had positive x direction here, positive y direction there, then we would normally measure our angle starting from the positive x direction going towards the positive y direction, wouldn't we, and around kind of that way there. That's the direction that we'd be measuring angles in. So this here would be our quadrant 1, this here would be quadrant 2, this would be quadrant 3 over here, and that would be quadrant 4 there. So important to be able to visualize that, particularly when we sort of remove the negative part of these axes. And when we measure an angle in this plane, we would be measuring in that direction there. So an acute angle would be in quadrant 1, obtuse angle in quadrant 2, and so on. Then when we add the z-axis, so the z-axis is going to be this one here, then we need some way of measuring angles that are kind of above the xy plane or below the xy plane. Alright, so I'm going to remove this and then kind of draw the axes in the way that we typically do. So as I said, we typically have our x-axis and our y-axis. We just show the positive sort of directions of those axes, and likewise we just show the positive z-axis. So what I want to do now is represent a vector here. So let's maybe draw a vector, we'll call that the vector u. And I said in the last video that often when we try and sort of represent 3-dimensional vectors on 2-dimensional page, we might actually draw a box fully around that. I'm not going to draw a complete box around that, but I'm still going to try and show the sort of dimensions here. So what if we went and then I think that's not too bad there. Now what I want us to see is that within this, let's draw a line across there as well. So hopefully that helps to represent the sort of 3-dimensional nature of where that point is sitting. Let's say this has a magnitude of r. And what I want us to see is there actually a sort of series of right-angled triangles in here. So we've got right-angled triangles sort of all over the place there. Now this here is going to be our, if we were going to write u is equal to xi plus yj plus zk, then this here would be our xi vector, if you like, or that distance there would be the distance x. This distance along here that would be the yj vector, so therefore we could say that distance to there was the distance y. And zk, well, this here would actually be our zk vector. It's not sitting on the z-axis, but it's the same vector. So that would be our zk vector there. So I'm going to say that that there is equal to z. And so in fact, if I wanted to, with my x and my y, I could sort of move them onto the triangles here and actually say, well, that's the length y, and that there is the length x, which of course is the same as this length here, x, and that's length y over there. Alright, so labeling things in that way. Now, if I'm going to talk about polar form in 3 dimensions, I've actually got the magnitude and I've got 2 directional components. So I have this directional component here. Let's call that the angle theta. That's the one that I'm used to, which is the angle in the xy plane from positive x measured in a sort of anti-clockwise or towards positive y direction. So that's still there. In polar form for 3 dimensionals, that has the name, or that is called the azimuth. Okay, so the azimuth, the angle theta, is the angle from x towards y. And by that, I guess I mean positive x towards positive y. And that, as we know already from 2-dimensional form, can be a value anywhere between 0 and 360. So it doesn't really matter whether I measure the one for 0 as 0 or 360. So theta can be an angle anywhere between 0 and 360. I could measure it as a negative angle if I wanted. Doesn't kind of really make much difference there. But then I've got a second angle in 3-dimensional form, and that's the angle above the xy plane, or could be below the xy plane if the z component's negative. And so I'll call that angle there phi, and that one is called the altitude. And altitude probably makes a little bit of sense there because it's kind of a height, or I guess we could think of it as a negative height or a sort of depth below the xy plane. That is the angle above or below the xy plane. Now, can you see that because theta can be any angle between 0 and 360, therefore the altitude will be a value simply between negative 90 and positive 90. So it doesn't need to go beyond 90 degrees. You might say, oh, it needs to go all the way to 180, but it actually doesn't, because theta can kind of swing right around all sides of the z-axis. Therefore, the altitude only needs to go from negative 90 to positive 90. Alright, so if we're trying to convert between polar form and component form, then we're going to use our x, y, and z in component form, and our r, our theta, and our phi in polar form. So we're going to say that the vector u can be written as, so in polar form it would be r theta phi. Oops. So that's always the order in which we express them. It's always the magnitude, then the azimuth, then the altitude. Important to know that because there's 2 angles. And of course u could also be xi plus yz. We've already written that above. So let's write it here in sort of column vector form. So there's our component form, our polar form, and we need to be able to convert between those. Okay, so first thing I want us to recognize here is that this here in our triangle, that part there of that sort of, well, it's part of both the horizontal triangles and the vertical right angle triangle, isn't it? So it's a fairly significant side there. So the length of that vector there, if I was to use cos of phi, then I would be saying cos phi in that triangle is equal to, well, the length of that side, I'll call it d, over the opposite side. So cos is opposite over hypotenuse. Sorry, not the opposite, the hypotenuse. So, sorry, cos phi is adjacent on hypotenuse. So let me just be clear, I'm calling this side in here d, so it's d over r. So therefore an expression for the length of that line, that d, or that yellow line, would be r times cos phi. Now that's pretty significant because then that gives me the hypotenuse of the triangle down here, which contains x and y. So what I'm saying is that r cos phi is the length of this side, which is the adjacent side to phi in this triangle here, but it's also the hypotenuse of the triangle which contains theta and x and y. So that's going to be fairly significant now in terms of kind of developing expressions for x. So using that, I could say now I could get an expression, for example, for theta. So now I'm working in this triangle down here, and I'm saying, well, cos theta is equal to adjacent over hypotenuse. So cos theta is going to be equal to the adjacent side, which is x, over the hypotenuse, which I've just said is r cos phi. So rearranging that gives me x equals r. Now it's going to be cos phi times cos theta, but I'd normally write the theta first. Alright, so x equals r cos theta cos phi. Likewise, I could say sine theta in this triangle here. Sine theta is going to be the opposite side over the hypotenuse. So that's going to be equal to y over r cos phi. So rearranging that gives us then that y is equal to r sine theta cos phi. We could write the cos phi first, but convention is just to write it that way. And then for z, if we now have polar form, we want to get z, we could just use this vertical triangle here and say z and r are the opposite and the hypotenuse to angle phi. So therefore we could say sine phi equals opposite over hypotenuse. So therefore z is equal to r sine phi. So that one's a little bit easier. Now, maybe slightly unfortunately, those rules or results there aren't given to us on the formula sheet. Let me just write them down here as a summary. So cos theta cos phi, y is equal to sine theta, sine phi, sine theta cos phi, and z is equal to sine phi. So you do either need to commit those to memory, or you need to have some way of, sort of developing them from, I guess, the diagram or from your sort of understanding of the situation. Going the other way, life is a little bit easier. So r is equal to, we sort of already know this one, x squared plus y squared plus z squared. We also know that tan theta is y over x, so that's really just from our two-dimensional vectors. And hopefully you can see from the triangle above that sine theta is going to be equal to z over r. Well, that's really just a rearrangement of this one here, isn't it? So remember, with this one we still need to be a little bit careful, make sure we kind of develop that from our, or that we're aware of which quadrant we're in. So we do a couple of examples for polar form in 3 dimensions. Maybe just before I do that, let me do a quick reminder of scalar product. And scalar product becomes really helpful, really useful in 3-dimensional form. Now you do have a rule for scalar product on your formula sheet. And there it is there. So that's giving you the scalar product in a geometrical representation. That's the first one here, where it's the product of the magnitudes of the vectors and the cosine of the angle between them. and then it's giving you in component form. Again, our formula sheet doesn't give you dot product in component form for two-dimensional vectors, only three-dimensional vectors, but obviously if we're two-dimensional vectors, we don't have an A3 and a B3, so we don't have that final term there. So remember, in component form, we just multiply the corresponding components, A1 times B1 plus A2 times B2, and if there's a three-dimensional vector, we add on the product of A3 and B3 as well. So if we were picturing that, we've got, a vector A, another vector B, the angle theta between them. Note that in both of those forms there, that is going to produce a scalar, isn't it? That's why it's called a scalar product. The dot product is called a scalar product because it produces a scalar result rather than a vector result. Now, we don't need to say too much more about that, except that the scalar product has some incredibly useful applications, and probably even more so when we come to three-dimensional vectors, is how useful these are. So when we think about what we can do with the scalar product, let's remember that we could rearrange. So for the first one, we could say, if we rearrange that first definition, angle between vectors, particularly in three-dimensional form, we could rearrange and say, well, cos theta is going to be the result of the dot product divided by the product of the magnitude. So if you've got two vectors A and B in component form, in I, J and K form, you can simply take their dot product, divide it by the product of their magnitudes, and you will have the cosine of the angle between them. And it's not easy to find the angle between three-dimensional vectors unless we have a result like this, so that's really useful. Also remember some very important results, so particularly the idea that if the dot product of two vectors is 0, it implies that they are perpendicular. Okay, so because the only way, assuming A and B are non-zero vectors, the only way that this result here could be equal to 0 is if that is 0, and that would mean that theta is 90 or 270, so they are at right angles to each other. We can draw a double-headed arrow on this, an implication there. If they are perpendicular, then it follows that their dot product must be 0. I can't stress enough how important that result is. It's come up probably on pretty much every external exam in some way. Also, worth remembering that the dot product of a vector with itself, and you can get this from using the geometric definition, the first one, because cos of 0 is equal to 1, so it's just going to be the magnitude of the vector times itself, or the magnitude squared. Alright, we need to do a couple of examples of converting between polar and component form, but I think given how long this video is, I might do that in a separate video, so I'll finish this one here.